Okay, now let us try to understand one more important aspect in the transformer, which is the power handling capacity of the transformer. You have the small transformers, the big transformers, the huge transformers, the oil cooled transformers, so on and so forth. So, you have transformers with varying sizes, right from small signal to very high power transformers. Now, what decides the power handling capability of the transformer? So, to do that, we need to understand the mapping between the electrical and the mechanical or the physical dimensions or physical dimensions of the transformer. Physical dimensions. So, you have the electrical parameters in terms of the currents, the voltages, the power, number of turns, N1, N2, so on and so forth. And to that we need to have some kind of a relationship with the physical dimensions of the core with respect to the core sizes, the sizes of the wire gauge and things like that one. So, what is that mapping and how is that done? Let us have a look at the transformer to understand, to get a better understanding of what are the physical dimensions that we are going to talk about. Let us have a look at the transformer to understand its physical dimensions. So, you see the picture of the transformer here. The transformer consists of the terminals there. So, in a practical transformer, the terminals are brought out, and that is where the coil windings are terminated by soldering. The rectangular solid block, that is the core. In this case, the core is CRGO, that is cold rolled grain oriented silicon steel, and as the steel is conductive, electrically conductive, we would have lot of eddy currents if we had a solid block of steel, as we discussed in the last class. So, to reduce the cross sectional area for the eddy current path and thereby increase the resistivity, to increase the resistance for the eddy current path, the laminations have been put. And see that all practical transformers will have the core, the solid bulk of the core, which is laminated, and then after laminating it is all air pockets are vacuumed out and then it is varnished. So, that black color or the darkish color is due to the varnish. Now, you see at the winding at the center, which goes through a central limb. Now, this consists of both the primary and the secondary. So, the primary is wound first and then the secondary is wound on that one about the central limb. So, the core here looks slightly different. Let me give you a better idea by drawing the two-dimensional view. The core will be something like this. So, we have this rectangular block, solid block, and then we have a central limb. We have a central limb. Now, the winding is done on the central limb here in this case. So, you see the winding is done on the central limb. So, let us say this is the primary and the secondary is also wound onto the same central limb. Like that. So, they are wound one about the other with an insulation layer in between. So, this would be the secondary. This is the E2, this is E1. Now, here of course, if I make it into an isometric 3D, this will look more like the transformer that we have here, and we have the terminals which are brought out here, and actually these points are soldered onto this. So, you could have these points which are soldered onto this, and the secondaries which are soldered onto this. And these are the laminations which you will see, the lines here, which are the thin laminations of the grain oriented silicon steel. Okay. Now, here you need to worry about few physical dimensions, which I will explain now. We will take that same core, we have the central limb, this is the 3-dimensional view of the core. So, we have the winding around the central leg. What is the maximum amount of windings that one can accommodate? So, if I cut, you will see that this is the number of windings that can be accommodated, both primary, secondary, all put together. So, what winding goes out will come out through this. So, it is the same loop. So, what goes out through here will come out. So, they have the current direction as coming out here and going in there. In this way. So, effectively we have this area only available to accommodate the windings. That is called the window area, AW. There is another important area that you need to bother about, and that is you have this of the central leg, or let me draw the other area which is also very important. And that is the core cross section area. Now, this core cross section area, let me show it in this different color. In this 3D image here, like that. Through which the flux are flowing. The perpendicular cross section area, that is the AC, or the core cross section area. So, we have two areas here. One is called AC, which is the core cross section area. Another is called the AW, which is the window area. These are the physical dimensions of the core. How will you map these physical dimensions to the electrical property? One is by the Faraday's law. So, this is linked using E is equal to N d phi by dt, this is the Faraday's law, this we know, which is equal to N AC dB by dt. So, if you see that for a given number of turns and for a core with a particular swing in the flux density, E is proportional to AC. The core cross sectional area determines the voltage withstanding capability for the transformer. How much voltage it can withstand, beyond which the transformer saturates, because beyond which the volt second product will exceed the flux density capability of the core, and the core will saturate. So, AC will tell you how much voltage a particular core can withstand. Then you have the AW. AW is related to the number of turns that can be accommodated in the window area, both primary, secondary put together. So, now that is going to depend on the thickness of the copper wire that you are going to use to do the winding. And the thickness of the copper wire is decided by what? It is decided by the currents flowing through the copper wire, because there is I square R loss and we can't have too much loss into the copper. And therefore, if we have I1, as the current flowing through the primary and I2 as the current flowing through the secondary, and let us say that J is the prescribed or the recommended current density that can be allowed in the copper. Normally, this is around 3 amps per mm square. This is a typical value. It can vary from design to design, power rating to power rating, but 3 amp per mm square is a typical value that one can expect in the copper wires of the transformer. So, what is current density? J, current density is I RMS by area of cross section of the wire. Area of cross section of the wire. So, area of cross section of the wire is dependent on I RMS by J, the recommended current density. So, you will obtain the A wire for the primary, the area of cross section of the wire for the secondary, based on I1 by J and I2 by J. Now, there are N1 number of windings for the primary wire, N2 number of windings for the secondary wire. So, N1 into its cross section area plus N2 into the wire's cross section area of the secondary, all these must fit into the window area, into the available window area of the core. Now, A wire is dependent on the RMS value of the currents. So, the current carrying capability is decided by AW. The voltage capability is decided by AC or the cross sectional area of the core. Therefore, the product AC into AW should decide or should give an indication on the power handling capability of the core. This is the area product AP. This is called the area product, and this should decide the power handling capability of the core. Because this is deciding the voltage handling capability, this is deciding the current handling capability, and therefore, this decides the power handling capability of the core. This is the electrical parameter which is trying to map to the physical dimensional parameter of the core called the cross sectional area of the core. Another electrical parameter, the current, RMS current, which is trying to map to the window area of the core, another physical dimensional quantity of the core. AC, AW and sometimes AP are given in the data sheets of the core. V and I are calculated from the electrical circuit, and by this mapping one can choose what should be the size of the core for a given power handling capability, for a given power of the power that has to be passed from the primary to the secondary. The sizes of the core will be decided. Now, there is one more important deduction that we could do from the already known formula that we have, and that is E, which is equal to 4.44 N AC BM into F. This is the standard formula, that the voltage induced formula that we have derived for sinusoidal excitations for a transformer based on the Faraday law of electromagnetics. Now, here for our mains, which is 50 hertz, we are using normally the most common types of core materials in the market would be especially for the 50 hertz frequency is the CRGO, which is the cold rolled grain oriented, or the CRNGO, the cold rolled non grain oriented, which is slightly less expensive. So, if we are using, let us say, CRGO, the cold rolled grain oriented, this would be around 1 Tesla as the design value. Let us say for 1 volt, for an AC of 1 meter square, we have 1 which is equal to 4.44 into 50 into 1 Tesla into 1 meter square into N. So, N is equal to 1 by 4.44 into 50, which is approximately 0.004 turn meter square per volt. this is for 1 volt, so many turns for 1 volt the area comes in, so that is the meter square per volt. This would be an approximate thumb rule which will give you at least a figure of what will be the order of magnitude of the turns that you would be applying. So, N is equal to 0.004 turns meter square per volt. So, let us say for E is equal to 230 volts and a core area which is 100 into 10 to the power of minus 6 meter square. This is the order of the magnitude of the cores, 100 to 1000 into 10 to the power of minus 6 meter square, which you will see the core cross section area. Let me take a value of 100 into 10 to the power of minus 6 meter square, easy for calculation, it is a small core. Then what is the turns that one would get, which would be 0.004 into 230 divided by 100 into 10 to the power of minus 6. This is approximately 10,000 turns. So, core of this size 100 into 10 to the power of minus 6 meter square core cross section area. If you want to apply 230 volts, you will have to approximately put around 10,000 turns to so that it can withstand that voltage and deliver the power from the primary to the secondary.